Hello again. So part B on a non-determinism. So when we left off with part A, we were talking about here the definition of non-determinism, the difference between the definition of non-determinism and the definition of a non-deterministic finite state machine, and the definition of a deterministic finite state machine is right here. Is that with a non-deterministic finite state machine, you're looking at the power set, you're looking at the output is not a single state, but instead is a set of states. Can be the empty set of states, can be a set that contains more than one state, so it's a set of states. You can go to more than one next state, or in fact go to no next state at all. Okay, so time for some examples. So here's, to contrast with the examples that I did when we introduced deterministic finite state machine, here's the non-deterministic finite state machine that accepts only those strings ending in HEF. And it's really just about as straightforward as it could be. You have here that the machine, just like the garage door opener, the machine just waits, and then guesses. That's the jarring part. Guesses that this is the end of the string. It sees an H, an E, and an F. Now, when we did this with the deterministic machine, we saw that it was possible to do this with a deterministic machine. Remember, there was something not tremendously complicated, but slightly complicated. When it sees an H, it goes to Q1. If it sees an E, then it goes to Q2. But then if it sees an H, it has to go back to Q1 again. And so there's a somewhat complicated, at least possible to get wrong, sequence of interactions. Look at the difference between the two machines. This one is just simply simpler. It waits and waits and waits, and then when the end of the string is coming, if it sees an HEF, it grabs onto it and accepts that entire string because HEF is the suffix. Okay, so the non-deterministic machine is much simpler. I mentioned that by the end of this slide, we're going to show you how to convert a non-deterministic machine to a deterministic machine. So you can imagine that given a job that looks somewhat complicated, you can do it in a non-deterministic way, then convert it to a deterministic machine, and in that way have two easy jobs rather than one hard one. Okay. So here's a non-deterministic machine with a finite alphabet that accepts an input string if and only if it has an A in the third position from the end. Now, to do this with a deterministic machine would be moderately complicated, but it's very simple with a non-deterministic machine. You have an A, and then another character, and then another character. That makes the A be the third from the end. How does the machine know when it's watching the input, watching the input, watching the input? How does the machine know when this is it? This is the A that's going to be third from the end to go over? And the answer is it guesses. Or you can imagine that it's told by some daemon it's going to be the fifth character. And then all the machine has to do is verify that the daemon told the truth. Now, one thing that I see happening sometimes with non-determinism is that people ask me, well, how could a machine be not accepted? So what if A is not the third character from the end? And so, for example, what if you got the string B, B, A, B? So the third character from the end is not an A. Okay, well, the answer is the point we made about existence, is that there is no way for the machine to guess this is the A and go right, because there is no A to guess on. There's no way to guess and be right. There's no answer a daemon could give you that would be correct, that would verify. It can't happen. So BBAB won't be accepted because there's no way for it to be accepted. Accepting is an existence statement. It says there exists a correct guess, but there is no correct guess, so it won't be accepted. Instead, the collection of strings that are accepted are just exactly the ones that are listed here in the language. You see, all of these strings have the third character from the end, third character from the end, third character from the end, third character from the end. Oops, we did it wrong. Third character from the end, third character from the end, third character from, you see what's happening. The third character from the end is, in each of these machines, is an A. So, for example, for this very last string, the machine guesses that it shouldn't go, and anyway it can't because the first character is a B, and then it sees an A and it kind of says to itself, could that be the A? Yes, I'm guessing it is, and makes a change. Is there a way for the machine to guess correctly? There is. and said in, again, a form that sometimes gives people a better sense, is there a way for the daemon, for someone, for some oracle to tell you, you should go now? And then it has to verify. You don't just take the daemon's word for it. You can't take a daemon's word for anything, but you verify that it works, and it does. And the answer is yes. There is a way for the daemon to tell you. The daemon can tell you. The second character here is the way, is the one to go right on. Okay. Here's a machine that with alphabet oops, I typed the wrong alphabet. I'm sorry about that. So the machine with alphabet here, 0, 1, sorry about that. Oops, typo, 0, 1, that accepts an input string only if it contains a substring with a 1, followed by any number of zeros, followed by a second 1. Okay, so a 1 followed by any number of zeros, followed by a second 1. So just as an example, here's a 1 followed by 1 0 followed by a 1. It has that such a substring. Here's a 1 followed by many zeros followed by a second 1. It has such a substring. And it's a non-deterministic device, so it says any here, including 1. So leaving Q0 is more than 1 1. So, but once it gets here, it sees that 1. It makes the leap to going right. It's allowed to accept any number of zeros, and then it sees a second 1. That's more reminiscent of the deterministic device. What's happening here, though, is like a non-deterministic. This is the non-deterministic sort of portion of the device. The whole device is non-deterministic, but this is the non-deterministic portion of the device because it's guessing when to go right. And again, very straightforward to write down. And in fact, the picture of the machine is pretty much just a description. So that makes it extraordinarily easy to write down. Okay, one more thing we're going to introduce with non-deterministic machines, and that is called epsilon transitions or epsilon moves. So we'll alter the definition of a non-deterministic finite state machine so that instead of having this definition here, instead of saying that it takes Q cross sigma and as input, and things from Q cross sigma as input, and then things from the power set as output. Instead, the machines are now going to be allowed to take characters that include this epsilon. Now I know that epsilon looks like the empty string, and there's some relation, but since things here are actually singleton characters, it won't be possible to confuse it with the empty string. So we'll use epsilon as the character here. The associated behavior is that the machine can transition spontaneously without consuming any input. So the machine could just jump from state 3 to state 5 if there's an epsilon transition between the two. Okay, and why are we doing that? And the answer is, just like with non-determinism, is that because it's useful in an engineering sense. So let's do an example. Okay, so on the left here is the machine that accepts strings. It's a non-deterministic machine. Actually, it's a deterministic machine too. But anyway, it's a non-deterministic machine that, oh, excuse me, it's only non. I'm sorry, I misspoke because it doesn't have any B here. So it's a non-deterministic machine that accepts strings with a prefix AB. Here is a non-deterministic machine that accepts strings with a suffix AB. I'm going to use the epsilon transition, the epsilon move, to put those two machines together. So I allow myself to jump from Q2 to Q3. I'll remark that I also changed Q2 to be not an accepting state. But anyway, I allow myself to jump from Q2 to Q3 if I want. So this machine can spontaneously jump, or transition on the empty string, however you like to think about it, from Q2 to Q3. Now, why? And the answer is because I now have a machine that accepts strings that begin with an AB and end with an AB. It's a non-deterministic device that accepts strings that begin with an AB and end with an AB. So you see, I'm building up more complicated things from simpler things, and that's always good in mathematics. So these epsilon transitions allow me to put together machines, put together simple things and make them more complicated things, and that's obviously an engineering, something desirable from an engineering standpoint. When you're trying to do the homework and you're given a complicated description, or when you're trying to write a network protocol and it calls for a complicated description, then you say to yourself, I want to be able to take some simple things and put them together in some organized way. That's what epsilon transitions do for you. What other things can it do? Okay, well, just a minute ago, it was putting things together so that one happened first and then the other happened. Well, here, that is to say, put them together so that they worked in serial. Well, here, they're working in parallel. Same two machines, prefix of AB, suffix of AB. Put them together in parallel. I add a state here. I add a state that has two epsilon transitions out of it, so I can spontaneously go from Q0 to Q1 or from Q0 to Q4. And what I get is a machine that accepts strings that begin with AB or end with AB. So this machine does an or, whereas the previous one did an and. Okay. One more thing that I want to express what epsilon transitions can do for you is that we saw when we first introduced finite state machines, we saw giving the any number of repetitions of HEF example. So here you can get that same sort of thing, AB and back to Q0, AB and back to Q0, AB and back to Q0. So by adding this epsilon transition, we are allowing ourselves to misspell the word language. We are allowing ourselves to do this any number of repetitions. So we're introducing epsilon transitions because they give us engineering advantage of being able to build more complicated things out of simpler things. Okay, so we've introduced non-determinism. We started with finite state machines. That seems to me people often say, yeah, I get it. We introduced non-determinism and we introduced epsilon transitions. And now the third thing we want to talk about is what I've been promising for a while now, is if you give me a non-deterministic machine, how do you convert it to a deterministic machine? And I'm going to do it in the simplest possible way. I'm going to do an example, and I think the example makes clear what to do. Okay, so the theorem is that if you give me a non-deterministic finite state machine, then I can produce a deterministic finite state machine that does the same job. That's what the theorem says. It says if you give me a non-deterministic finite state machine, then I can recognize the same set of languages. The class of non-deterministic finite state machines recognizes the same set of languages as a class of deterministic finite state machines. You don't have any question, given a deterministic machine, can you make it a non-deterministic machine? It is already. It's a sort of a default non-deterministic machine. The question is the other way. If you give me a non-deterministic machine, can I make it into a deterministic machine that does the same job? And so I'm going to do that with a piece of paper. Let's see how we do here. If I move stuff around on my desk here, I didn't want to do that out and make it too long. So let's see here, and unclick. Okay, this paper here. These machines, sometimes they're a little weird. That kind of a click, 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 click thing is a little weird, but that's what we're going to go for. And I think I can get some additional light on the subject here. Let's see. Okay. Okay, so I'm gonna write down a non-deterministic machine. I don't want to write one that's too big because you'll see these machines get bigger when you do the construction. But nonetheless, it's a non-deterministic machine, and I'm going to convert it to a deterministic machine. Let's see how I do. So in my notes here, I have Q0 and Q1 and Q2. And Q2 is an accepting state. Okay. I already put in one of the edges. That's a B. There's a loop here. Show you what to do with a loop. There's an A that goes down and a B that goes back. And there's a loop here. So just a variety of things. I happen not to have any epsilon transitions. The book talks about epsilon transitions. Happen not to have any epsilon transitions, but nonetheless, clearly a non-deterministic device. I'll draw that on the table just to have drawn the table here. Let's see how we do. So the delta table, AB, Q0, Q1, and Q2. Okay. Okay, and let's see if I get it right. Always a big one. So if you're in Q0 and you see an A, then you go to Q1. But remember that the definition of non-deterministic device is you go to a member of the power set. So it's actually the set Q1. If you're in Q0 and you see a B, you go to the set Q2. Oh, I forgot to mark Q2 as an accepting state. If you are in Q1 and you see an A, then you go to both Q1 and Q2. So Q1 and Q2. If you're in Q1 and you see a B, then you go nowhere. Empty set. If you're in Q2 and you see an A, then you go nowhere. If you're in Q2 and you see a B, you go to singleton Q2. Okay, so not supposed to be too complicated, just want to make a simple example. Now I'm going to convert that to a deterministic device. So I'm going to have a big table here, and it's going to involve, I guess I need a little bit of room here. It's going to involve the inputs A and B, and it's going to be a deterministic device. Happens that it's a little bigger. So I'm going to list down here all the possible sets of states. So just to start listing, the set that's empty, the set that contains only Q0, the set that contains only Q1, and the set that contains only Q2. And maybe I'll put a little line there so that a person can read the table. And further down, the set that contains Q0 and Q1, the set that contains Q0 and Q2, and the set that contains Q0 and Q3. And finally, down here, the set that contains all of them. Oh, I said Q0, Q3. It's supposed to be Q2. Sorry about that. What happened? Oh, Q1 and Q2. Q1 and Q2. My goodness, trying to do too many things at once. All right, and then the set that contains all of them. Q0, Q1, and Q2. Okay. I'm going to want to refer to these guys, and I'm not going to want to refer to them by what they are. So I'm going to give them new names just for convenience. So I'm going to call that S0. That's going to be S1. That's going to be S2. S3. S4. S5. S6, and S7. Okay, it just gets to be too much writing. Okay, so let's see, remembering the original machine. Okay, so what's going to be the start state? Well, it's going to be, since I started in Q0 here, the start state of this machine is going to be the one that contains only Q0. You remember the first time I did non-deterministic devices, when I did that example, I started in just Q0. That's where I started. Okay, so that's going to be the start state. Maybe I'll put a little arrow indicating that it's the start state. I didn't make a very good naught, did I? Naught. Okay, so up here to the table. If you're in Q0, just Q0, not anything else. If you're in Q0 and you see an A, what happens to you? Well, again, if you cast your mind back to that example of a non-deterministic device, if you're in Q0 and you see an A, only one thing happens to you. You go to just Q1. Just Q1 down here is called S2. So S2. Right? That's it. If you're in just Q0 and you see a B, then you go to, if you're in just Q0 and you see B, then you go to just Q2. Just Q2 is called S3. So S3. And of course, I'm going to fill in what happens on that line. I'll fill in the other lines. Can only do one thing at a time. If you're in just Q1 and you see an A, then you go to Q1 and Q2 both. So Q1 and Q2 on this table is called, Q1 and Q2 is called Q6, excuse me, S6. So S6. Back up. Sorry about the sliding. I should have made a bigger picture. If you're in just Q1 and you see a B, then you go to the empty set. The empty set on this on this table was called S naught. And you see the idea here. If you're in just Q2 and you see an A, then you go to the empty set. That's called S naught. If you're in just Q2 and you see a B, you go to just Q2. That's called S3. Go up. If you're in, I don't think I can get it all in the same picture at the same time. There we go. That's probably about the best I can do. If you're in both Q0 and Q1, if you're in both Q0 and Q1, and you see an A, then you will end in Q1 and Q1 and Q2. Taken together, it's Q1, Q2. So again, if you're in both Q0 and Q1 and you see an A, then you will end in, you think about that example that I did, then you will end in Q1 and Q1 and Q2, and when you throw out the repeats, because sets don't have repeats, then you end up in Q1, Q2, and I'm calling that S6. Okay, and that's the only hard step. That's the only step where a person would say, what happens here? Let me fill in the rest a little more quickly. So I got here S3. My notes say S3, then S2, S3, then S6, S3, and then S6, S3. And you should obviously check my check my work because I make a lot of mistakes, but I think that's right. And then finally up here, what does a person do up here? And the answer is that if you're nowhere and you see an A, then you just stay nowhere. You're still nowhere. And if you're nowhere and you see a B, then you're still nowhere. And again, you think back to the machine that I drew, and it had some of the branches died and just stayed nowhere. That's all. Okay. Okay. So what I end up with here is I end up with a deterministic device. That's, to tell you the truth, that's really why I put the S's in, because it makes it clear that this is a deterministic device. You end up with a deterministic device that does the same job. It accepts the same strings. Well, which strings does it accept? What are the accepting states? Well, remember all the way at the top, Q2 was the only accepting state. So down here for this machine, we'll take any state that includes a Q2. Any state that includes a Q2, any state that includes a Q2, and any state that includes a Q2, and make that accepting. Very good. Okay, so what we end up with is a machine that will accept the same strings as the original one, but is deterministic instead of non-deterministic. Now, don't get me wrong; it's got a lot of states. The original machine had 3 states. This one has 2 to the 3 states, because that's how many subsets there are. But nonetheless, it's a deterministic device that accepts the same strings as the non-deterministic device. So the non-deterministic device is not totally useless. You can think of it as an engineering, here we go, think of it as an engineering choice where you write down the non-deterministic device because it's simple, and then you convert to a deterministic device. Isn't it clear you can write a program to do that? You convert to a deterministic device, and then you're happy. Have a deterministic finite state machine. Okay. All right, very good. So, a part A and a part B. This is the second part. So we've worked through finite state machines, and we also have the bonus of having some sense of non-determinism. Very good.